Bismillahirrahmanirrahim. Hello everyone. I hope you are all doing well. Ramadan Kareem to all of you and to your families. Our topic today will be about seismic migration. I will be talking about the migration. I will try to go to some theoretical background of the migration, and then we will see why we need the migration, and also we will be going through the different types of migration from the very basic one to some very advanced one. And lastly, we will see some real examples and real applications. So the migration, as I have mentioned already in one of the lectures, is a part of imaging, because we have already seen that seismic data processing can be divided into signal processing and into imaging or into image processing. So after stacking, we will be starting what we call imaging. In the imaging, we will try to correct the, the seismic events and to put them into the correct locations, because we have learned that seismic does not do that, and seismic does not give us the correct image of the earth, but is kind of distorted image of the earth which needs further corrections. So we have many different types of migration. Some of them they have the name of the the one who has introduced them. Some of them they have the name of the, the mathematical approach which is involved in that approach or in that process. We have a migration which are performed in the data before stacking, so we call them pre-stack migration. Some of them they are performed after the stacking, we call them post-stack migration. Some of them they are run in time domain, some and others they are run in depth domain, so we call them depth migration. And each type of migration, whether it is time migration or depth migration, pre-stack migration or post-stack migration, they have limitations and they have advantages against each other. So why we need the migration? The migration is actually needed because we have learned that seismic stack sections which we obtain after the animal corrections, they will produce or they will give us a fake image of the earth or distorted image of the earth which we cannot rely on and we cannot trust. There are too much distortions, and these are some examples. So for example, if we have an isolated body, it will appear in the stack section as a hyperbola shape. If we have a dipping target, it will be appearing longer and with a different dip than the actual dip in the true or in the real earth. So after doing the migration, everything will get back to its origin and its correct shape and dimension. So but how do we do that practically? Practically we are doing the migration since the 1930s and 1940s with the help of what we call the manual migration or the Hagedorn migration. This migration is very basic and very simple. So what do we do in that migration? If we have a time section or we have an event in the time section, we believe that the seismic response is actually, which is part of this event, is actually coming from any point in a semicircle, but it's not from one single point. So it's actually the the problem has many solutions. The same thing for any point belonging or any point which is part of this line. So any point in this line, it can come from any point in a semicircle which will pass through this line or this point. So by drawing semicircle at every point in this event, and we if we track the line which will be produced by the constructive interference of these semicircles, we will end up with having the migrated event. So this will produce for us the migrated event. So this one is before migration and this one is after migration. So the migration actually, or this movement or this displacement has um, a long effect or a large effect on the data, and we will see that there might be a very big displacement actually before the data, before the migration and after the migration. We will have lateral movement or lateral displacement, which we will denote it as dx. We'll have also a vertical displacement will be dt, and we will have also a change in the deep. So the displacement can be so large, and it can reach kilometer in range. So for example, here we have an example here where we have migration. We have some numbers here, and the displacement can reach, for example, in this example, 6 kilometer. So what does it mean? This, it means if you have a target or you have a dipping event and you want to drill it based on your stack section, you will find actually that the, the actual point or the real point or the real target which you want to drill is 6 kilometer far from the point which you have in your stack section. And this shows that it's very important to do some corrections and to do something in order to bring it back, which is the work of the migration. So, and this is telling us also that we have to acquire our seismic data in very long and very large spatial coverage, and we have to take some consideration into our um, acquisition. We have to do some precautions, and we have to have a large spatial coverage in order to have our displacement or our displaced events uh, should be located in the same or in the image which we got from the seismic. And also we have to get very good signal to noise ratio, because this will improve the result of the migration and will produce a better imaging conditions and data and results. We have to have also a good spatial sampling in order to avoid any kind of aliasing. And aliasing, we have seen that it's a kind of having different form of the real event because of nothing but the wrong sampling or the undersampling. So having good sampling, it means we will be sure that the image which we have now is the correct image of the target or the object. So for example, here we have a real example. Here we have a fault which is in the stack section, but after we do the migration, we will not find it. It will be out of the section. Why is that? This is because we did not acquire the seismic data with sufficient coverage. So the target now is out of the section, and we know in interpretation how important are the faults. They can be migration path for hydrocarbons, they can be also forming traps, structural traps in front of them, and we can find hydrocarbons are accumulating there. But by doing the migration, all these will be out of our image. So now let's see some conceptual models behind modern migration techniques which we are using in oil industry. If we go to the first conceptual theory, which is the diffraction summation. The diffraction summation is very important in many different types of migration. So what does it mean, the diffraction summation? We will start by an example. We have here, for example, a harbor here, or an area which is close to the beach. If we can imagine that we are living here or we are near to the beach, and um, there is a barrier which is separating between the ocean and between the harbor or the port. So, and here in this space, the ship, the vessels or the boats, they can enter the area which is quite calm from any ocean waves or from any storms. So when the wave is coming from the ocean, it comes as a plane wave, but when it comes and when it will enter the this entry point, it will be like a spherical wave. So, and here we will have wavefronts which will propagate and will get spread and will get large and large as we go from the source. And this is what is happening exactly in seismic acquisition. So if we just increase the number of entry points, well, what we will have many diffractions or many wavefronts. Those wavefronts, they will interfere, they will superpose. We will have some constructive interference and we will have some destructive interference. Where we have constructive interference, we will have large amplitudes. And when we will have destructive interference, like the case uh, in the internal part of the curves or the wavefronts, the amplitude will get weaker and weaker until they will vanish. And this is in this cartoon we see that at the edges we have isolated, or we have only hyperbola shapes without interference, so this will survive. But all the edges which are subject to interference, they will cancel out and they will get weaker and weaker. If we increase the number of entry points by reducing the spacing between the points, so what we will have more interference and more interference. And if we will leave very large entry interval, which we will suppose that is nothing but is an infinity of entry points, so we will have um, an interference between the wavefronts, which will make and will produce like an event which is straight, which is like a linear event and continuous event. And how this is happening is that this is happening exactly with the same mechanism by simply the interference between many wavefronts. So from now on, we can just imagine that the seismic, which or the seismic events which we have in seismic sections, they are nothing but they are superposition or they are interference of many diffraction points. So whenever we have um, a scatter point or a diffraction point, we will have a hyperbola shape which will be produced by the energy which is propagating from all directions, and they are coming from this point. So the energy will come to this point, and because this point is smaller than the wavelength of the wave which is coming to this reflector, so the energy will propagate in all directions. And when the energy will propagate in all directions, we will have exactly the hyperbola shape which we have already seen an example of it in the NMO correction. So now we will go back to our seismic. Let's imagine that we have one single diffraction point. If we have one single diffraction point in the acquisition, we will have a hyperbola shape. But if we have many points, we will have many diffraction points. If we have many diffraction points, we'll have many diffraction curves. We'll have many hyperbola shapes. The hyperbola shapes will interfere and they will get superposed and they will interfere constructively and destructively. Once they are constructively interfered, we will have uh, strong amplitudes and strong reflections. And once they are destructively interfering, they will cancel out and they will get weaker and weaker. So actually, what do we get from the seismic is that one we get from the acquisition or from the processing and after the stacking we get these events with this kind of hyperbola, and we can observe this kind of hyperbola shapes or diffraction curves in any discontinuity point, like at the edges of the faults, like at any isolated bodies, or at the edges of maybe the discontinuities or unconformities. We can see this kind of diffraction points. So with the help of the migration, we will aim to collapse these kind of diffraction curves and hyperbola and to bring them back to a point. This is another example where we have many diffraction curves which are superposed and they are constructively interfered, and we have a good seismic event. So this is the true one, and this one is the theoretical one. This one is actually produced by simply the interference and the superposition of the diffraction curves which are coming from all the points in this event. So we are seeing that we have exactly the same features and the same characters, except at the edges we have diffraction curves. So the migration will try to collapse those points and to bring them back to a punctual shape. And the first one, or the first migration, which was run using the diffraction curve, was the Kirchhoff migration. The Kirchhoff migration is taking the name of the Gustav Kirchhoff. He is a German physicist. While using his summation or formula of the summation of amplitudes, and is actually coming from optics. So this summation formula is actually summing all the amplitudes along this hyperbola shape or this diffraction curve and putting them or putting the sum of all the amplitudes at the apex of the the diffraction curve. And we see here that this summation is actually treating the amplitudes at the diffraction curve differently, because here we have the amplitude are getting weaker and weaker at the edges of the hyperbola or at the edges of the diffraction curve, and theoretically it should go to the infinity and the amplitude will go to zero. But we see that the amplitude will get stronger and stronger as we go to the source, or we go to the center of the hyperbola shape or to the apex of the hyperbola shape. So once we do the summation or the the Kirchhoff summation is taking the amplitudes, the weaker one and the stronger one, and summing them all to the point at the apex. And this is the migration. So in the migration, we will try to collapse all the diffraction curves here and to bring them to a point. And at this point, we will have all the amplitudes which are distributed over this diffraction curve. And this is the physics or the theory behind the Kirchhoff migration. So the Kirchhoff migration is nothing but a summation of the amplitudes along these diffraction curves and bringing them all to the apex of the diffraction curve, because we are assuming that every point in the seismic event which we have in the stack section is actually nothing but is a superposition of many diffraction points. So at the end, we will have uh, a displaced event or a migrated event which is similar to the one which we have obtained from the, um, the Hagedorn migration or the manual migration by simply drawing semicircles which will pass through every point in the event or in the stack section. So the migration of Kirchhoff or the Kirchhoff migration is actually depending and is affecting too much, is affected by the velocity which is used. And that's why we need to have a very good velocity, similar to the case of the NMO correction. The NMO correction, we have seen that if we have larger velocity or lower velocity than the actual velocity or then the right velocity or the appropriate velocity, we will end up with having curving up or curving down. So here it's the same thing in the migration. If we have lower velocity than the appropriate velocity, we will have curving down of the event. And if we have the appropriate velocity or at least approximated velocity, we will have a point, because all the amplitudes which is distributed over this curve or this hyperbola curve will be summed all to one point. If we have a velocity which is larger than the correct velocity, then we will have curving up or smiles. Sometimes we call them migration smiles. So that's why doing a very good velocity analysis or migration velocity analysis to avoid this kind of distortions or artifacts sometimes is very important. And that's why um, the velocity, the migration velocity analysis is so important to ensure that the velocity is accurate and is doing the job. So another thing which we have to put in mind that actually we cannot collapse all the diffraction curves, because this will take too much time. You can imagine if we have many seismic events along very long offsets. So usually we have migration aperture or spatial aperture. In this special aperture or window or migration window, usually we try to limit how much we will do the diffraction summation. So we cannot go to the infinity, because theoretically these kind of diffraction curves, they go to the infinity. And also we define an angular aperture. So with the help of this angle, we can limit the intervals where we will do the diffraction summation, and we will save too much time, because there are some data which we cannot do that for them. So we we can do like in the NMO correction, we can just mute them, because there is no need to use all this data set. So we will just try to define the zone which we are interested in order to do the diffraction summation and to perform a good or a very good migration. An advantage of the Kirchhoff migration is that we can run it at any interval we want. We can define an interval or a window of interest, and we can run the migration only over the window which we are interested in. It's not like other migration which require the entire data set in order to run the migration, because we have mentioned that the migration is actually kind of multi-channel process, so it will require um, too much data set in order to be run. So the kickoff migration is actually very flexible. So if we want to do the migration only for a small portion of the data, then we can just define the zone of interest, and then we can run the migration over that zone. Now we will move to another theory or another concept or conceptual model which will explain or will give an explanation for the seismic images or the seismic data, because the fraction summation is nothing but is a kind of explanation of the seismic image, how they are produced. We have another explanation and we have another theory which is explaining how the seismic image can be made or can be produced. This other theory, we call it or is named the exploding reflector. It was introduced by John Claerbout. He's a professor at Stanford University. He's very famous and he has many books in the internet. He's giving them free of charge. Um, the exploding reflector is saying that the seismic image or the stacking or the stacked seismic image which we are getting and we are collecting from the field by having source and receivers at the same locations after the anemone corrections and after the stacking, it can be simulated in another way. We can simulate it in a way that we put all the geophones on the ground and we put the sources on the reflector itself. We put the sources in the subsurface. They are kind of virtually experience. It's kind of virtual experience. So we put, it's like we are putting the sources on the reflector here, and we are shooting and we are exploding the energy from every point in the source at the same time. So the energy will be recorded by the geophones or by the receivers which are on the ground. So theoretically, this will give the same thing as we do in the stack section. So this is an explanation of the, the seismic waves, how they are producing an image for us in the stack section. So the exploding reflector is saying that we can get almost the same thing, but since we have only one way, which is the wave will take, so here we will use half velocity. We will not use the full velocity because here actually we have two-way travel time, but here we have one way. So we will not halve and we will not manipulate the time, but we will suppose and we will assume that the velocity here is the half of the velocity here, and we can have the same results. So, and if we believe and we trust and we assume that the exploding reflector theory is correct, then the migration will be nothing but it will be a wave equation solution. How is that? This is the wave equation as it is known from other science, not only in seismic, but from physics, from electromagnetism, from magnetism. So we all know this is the wave equation. So the wave is propagating in x, which is offset, in z, which is depth, and in time, which is t. So, and actually, what do we acquire and what we have in hand? We have the seismic section. The seismic section is actually a kind of solution, is already a solution of the wave propagation, but it is the solution when the z equal to 0, because the data is acquired using geophones which are coupled with the ground, and they are located on the ground where the depth is 0. So this is a solution. Actually, the image which we have from the seismic is actually a solution of the wave equation, but as at 0 depth. So what we try to do, we try to solve the wave equation, but at 0 time, because we believe that at the 0 time, the seismic energy was at the exploding reflector. So if we do that, we solve the equation and we found the, the solution at t0, or at t equal to 0, or at the 0 time, then this will be the migrated section. So it's simple and easy. So for that, we have many migration which are using the exploding reflector theory as the migrations which are using the diffraction summation. So we have some group of migrations, they are using as an assumption the exploding reflector. Some others, they are using the diffraction summation. So we have a migration which is called wave equation migration, and this migration is using the exploding reflector theory, and is assuming that the seismic wave is a kind of an energy which is propagating from the exploding reflector and is recorded by the geophones which are on the ground. So if we can find a solution of the wave equation at different depths, we already have one at the z equal to 0, or at the 0 depth, we find the solution or the iterative solution at delta z, and then we increase the depth until we go to the target. At the target level, or at the diffraction, or at the point, or at the reflection point, or at the reflector, the diffraction curve will collapse, and then it will be a point. So this is the theory behind the wave equation theory, or the wave equation migration theory. So it's quite simple. So we have seen now that in both migration techniques or approaches, our aim is to bring back the diffraction curves into their locations if any point in the seismic event is a kind of diffraction point. So now we have another migration which is using the FK domain. We call it the FK migration. This FK migration is quite simple also, is simpler than the two other migrations. We have already seen the FK and how it operates and how it works. So um, we have a seismic event in a seismic section which has a deep of alpha. So if we move to the FK domain, in the FK domain, all our events which are deep in here, they will have the same apparent velocity. And as we have seen already in the manual migration or the Hagedorn migration, actually the migration will convert any target with a deep alpha or apparent velocity or apparent slope with a slope of alpha to another event with a dip of beta, and the relationship between the alpha and beta is that the tangent of alpha equal the sine of beta. So if we have now the deep angle of the apparent velocity in the FK domain is alpha, by simply convert it to sine of beta, because now the tangent of alpha is already known, we try to find the beta which will give us the solution of this equation. Then if we find the beta, we will just try to rotate the event to the beta instead of the alpha, and then once we do that, we can go to the inverse Fourier transform, and then we can have the correct deep of the event. Lastly, now we move to the pre-stack migration. The pre-stack migration, they are a little bit more advanced than the post-stack migration, but they are kind of an extension of the theory which we have seen in the post-stack migration. So the concept behind the pre-stack migration, we have seen in the post-stack migration or the zero offset migration that reflection which is recorded on the seismic trace, it can actually come from any point in a semicircle. This is what we have seen in the manual migration or the Hagedorn migration. So now, because the offset is not zero anymore, we will have an offset term which will be involved in the equation. And instead of having a semicircle, now we have an equation of an ellipse. So the, the response which we are recording in the pre-stack can actually comes from any ellipse, but not a circle. And this ellipse shape is actually changing with offset. So at every offset, because we see that and we know that in the pre-stack gathers we have different traces recorded at different offsets. So this ellipse shape will change with the offset. So in the 3D 3D migration, we will have an ellipse in 3D also, and the offset will change in all directions, and then we will try to collapse this 3D ellipse to one single point. Now in the Kirchhoff migration or the pre-stack Kirchhoff migration, we have almost the same thing. We have seen already that we are trusting and we are assuming that every point is a kind of, every seismic event is a kind of an unlimited number of diffraction points, and every diffraction point is creating diffraction curves. So the diffraction curves actually, which we have seen in the post-stack or in the zero offset um, migration, they are kind of very nice hyperbola shape where the offset term is zero. But now, because the offset term is not zero, so the hyperbola shape will change with the offset term. And in the 3D, if we are moving in 3D, we will have a 3D hyperbola shape, and this will build actually a pyramid in the 3D. And this pyramid, we call it Khufu or Kofu or Chops pyramid. Is very well known in seismic migration, in pre-stack migration. So this pyramid can be obtained in the 3D pre-stack migration. We will just try to collapse it and to bring all the amplitudes which are distributed over this pyramid to one single point, which is at the summit or at the top of the pyramid, or it is at the apex of the hyperbola if it is only 2D. So how do we do the pre-stack migration or the Kirchhoff pre-stack migration? Usually we just try to separate the data into a constant offset, and at every offset we try to collapse the diffraction curves and we try to bring them all to point. We do exactly like what we have done in the post stack, but here we have an offset term, so it will change, the shape of the hyperbola will change at every section. Why? Because of the offset. But at the end, our main objective is to bring all the amplitudes which are distributed over this curve to one single point. And lastly, we will have migrated sections. Once we will have the migrated sections, then we can take out all the traces according to their locations or the CDP locations. And if we do that, we will have, and we can reconstruct again our pre-stack gathers after the migration. And from now on, we will call them common image gather. Why? Because they are already collected and they are migrated, and now they will be called uh, common image gathers, not simply CMP gathers or short gathers or CDP gathers. Lastly, the reverse time migration. Reverse time migration is one of the famous and the very widely used pre-stack migration. It requires too much computation power and uh, imaging. It requires also quite a lot of theory compared to the previous migration which we have seen. So what do we do in this migration? In this migration, we have two propagation. We have downward propagation of the seismic wave, or forward migration or forward propagation, and we have a reverse propagation. So the forward propagation is actually used with the help of a theoretical velocity model and the theoretical or synthetic gathers. So we try to build theoretical gathers or synthetic gathers using the normal way of propagation which we know and which we have seen. But the other one, which is the reverse propagation, is actually we are using the real shot gathers which we have recorded, but we will try to reverse back the time. So because the data which we have, they are recorded at X time or at T time, for example, 2 second or 3 second or 4 second. I have 4 second gathers. So what we will try to do, we will try to do as we have done in um, the wave equation migration previously, but that migration, it was only one way wave equation, but here we have two-way wave equation. So here we will try to solve the equation at different time, starting from the Tmax until the T0. So here, for example, we see at the time 50 millisec, we see the the wave equation here when it is propagating, and here we see the wave when it is propagated upward. So here we are using the real gathers, and here we are using the synthetic gathers. And then what do we have here? We have the cross correlation of the two events or the two animations, or the two solution actually of the wave equation. The forward solution, the forward propagation solution, and the reverse propagation solution. So we do the cross correlation of them, and then we get a product from them. And then we do the same thing for every time sample or every time interval. We try to solve the wave equation as we have done in the in the wave equation or the one-way wave equation. So here in the reverse time migration, we try to do that at every time sample or at every time interval, and we try to have both solution in the forward propagation and the downward and the reverse propagation, and then we get the cross correlation, which will give us the exact location of the seismic event which is responsible of these upward and downward continuation. And lastly, when we sum all the products which we have obtained from all the seismic event, then we will have the migrated section or the migrated image using the pre-stack migration. So it requires too much computation and too much theory, and too much solution in order to provide the solution of the wave equation, or in order to produce the migrated image of the Earth. So the in terms of computation is very expensive, but in terms of complexity, it will solve too much problems if for very complicated Earth models and for very complicated geology, unlike other maybe simpler migration, which maybe will fail actually against complexity in geology. So here are the steps which we are using in the pre-stack reverse time migration. The first time or the first step is build forward model by forward modeling of the wave field through an appropriate velocity model, which we can get from the processing from the velocity analysis. And also we can have the back propagation of the measured data, because we already have gathers which we have collected. So these are the measured data. So we will do back propagation in time, and then we will do the superposition of both using an imaging condition. What do we mean by the imaging condition? The imaging condition is nothing but is the cross correlation of the source wave field and the receiver wave field, which are here. So this one is the source wave field, and this one is the receiver wave field. So this is an example of the RTM, or the reverse time migration. This one is pre-stack kickoff migration. This one reverse time migration. We see that it can produce very high quality data. We see here, for example, the faults, they are very clear. But we cannot see them here in the image, which is obtained from the kickoff migration. So, and this kind of migration is widely used nowadays, especially in areas where there is salt domes, and we are trying to image the subsalt intervals, or intervals below the salt, because um, there are many reserves, huge reserves, which have been discovered below the salt, and this was impossible before. But now, with the help of the pre-stack migration and especially the RTM migration, we can image what is below the salt. Some examples and some applications of the pre-stack migration and the post-stack migration, time migration and depth migration. So because we have very long list of migrations, and those migrations, they perform at different domains and at different and under different assumptions. So which one will be applied for which scenario? So if we have simple velocity and simple structure, simple velocity means we believe that that the velocity is increasing with depth, and simple structures, all the layers are continuous and there is no problem. So in that case, we can use the post-stack time migration. But when things start to be complicated, like complicated and complex velocity, so here the velocity is not following the normal increase, but it will increase and decrease. So this will create a problem for the migration, and especially for post-stack time migration. So we will use post-stack depth migration. When we have discontinuities, then here we will need to have deep corrections, DMO and pre-stack migration. So here we will have pre-stack time migration. We will need to use it in order to correct these kind of discontinuities and these kind of deep changes. In the case where we have complicated velocities and complicated structures, then we will move to pre-stack depth migration, like the RTM and like kickoff pre-stack depth migration. So the RTM is not time migration, but is depth migration. So here we have an example. We have here a real Earth model or true model. We will test different migrations. So this is the image of the seismic from the stack. So we see that the image is too much distorted. If we apply the time migration, it will try to solve the issue. But here we see that the velocity is increasing, uh, and then it will decrease, and then it will increase. So here the time migration will fail and will not uh, be able to produce the correct image. But if we run the depth migration, then the depth migration will be able to treat and to handle and to deal with this issue of velocity inversion or velocity reverse. This is an example of post-stack depth migration. We see here that uh, it could do some good job, but there are many missing information which could not be treated properly with the help of the post-stack migration. So the pre-stack migration can do that job. And we see that here, for example, we see the fault here, and we see some features here which are not available clearly here. We see also some events which are having different characters compared to the one which is here. So, and we will trust more the pre-stack depth migration than the post-stack depth migration. Lastly, this is the different types of migration over time from the 1980s to the 2000s and onwards. So in the early days of the migration, we used to do the post-stack time migration. Then, with the complexity of the geology, now we're moving to, or we have already moved to pre-stack kickoff migration. And then, as the complexity has increased, the pre-stack kickoff depth migration was introduced and was used and has shown very successful applications. And with the increasing complexity, many migration approaches have been introduced and have been used, and one of them is the reverse time migration. For the reverse time migration, now we have many different, maybe sub techniques of the reverse time migrations, and all of them they are aiming and they are hoping and they are trying to solve the complexity of the earth and the complexity of the geology of the earth. Thank you very much for your listening.